in the arteries. Qualitatively, for quantitatively, we can see how the static pressure distribution changed along the line if the inlet pressure was changed from 0.75 times to 2 times in the stented artery. We looked at the static pressure on the stent, differential pressure across the stent in case of the stented artery and the normal artery at the same distance, and we could see that the stented artery is exhibiting completely different behavior in this particular case. We looked at the velocity magnitude and the velocity profile that we saw along the length. Because of this pressure is higher, velocities are going to be higher at the center line, and then we plotted the velocity magnitude along those planes in the stented artery at 3 different pressure inlet conditions. So if pressure is higher at the artery, how it will affect the flow inside the stented artery that we have seen. And then we calculated wall shear stress on the stents under 3 conditions, and the wall shear stress values were calculated, and you can see as the P in is increasing, blood pressure is increasing, things are becoming more complicated as things are getting along. Okay, and then we use 2 parameters, vorticity magnitude and the Q criteria, to see the rotation effect, and we reached at this particular point fault diagnosis in cardiovascular system. So we have analyzed the stented artery. Now we want to see if suppose plaque formation has taken place in this stent. So plaque formation has taken place in this stent. What will happen now? If we can we get some information about the plaque formation from the fluid dynamic data that we have in the arteries? Can we use fluid dynamic data as a predictive tool to calculate amount, location and severity of plaque formation across the stent? Can this information help us in developing stents which are smart, okay, which can take corrective action for the plaque formation? So what I have done here is I have taken normal artery without any plaque formation, and then I have taken arteries with plaque formation. So very small plaque here, area of plaque, bigger plaque area. So plaqued artery 1, plaqued artery 2 and plaqued artery 3. So the cross sectional area, as we see in meter square, this is what we have taken: normal artery, plaqued artery 2 and plaqued artery 3, and we will simulate the flow and see what happens to the flow behavior when a plaque has formed over the stent. Okay. So how do we create it? For this purpose, in the design modeler, first unfreeze the arteries, go to create primitives and create spheres at following locations. So what is happening is, near the stent I am creating spheres: small sphere, big sphere, biggest sphere. So spheres are created. You are at your liberty to choose any type of shape you want. Okay, I have created sphere because it was easier. You can create ellipsoid, you can create planes, or any type of thing you can create on the artery. Then freeze the arteries again, design modeler, update the mesh, open fluent, specify boundary conditions, go to solution initialization, and then run the solver. So same thing, same process, except you are creating 3 spheres as I have shown here at these points, only a part of a sphere. Okay, so just do this and then you have faults created. Now you will now notice the effect of plaque formation can be quite severe. So what I have shown here is the normal artery, and when a plaque has formed in the artery, and you can see the pressure has gone very low here. The plaque 3 artery pressure value has gone very low. So when plaque formation takes place, probably pressure will be affected, velocity will be affected. So as plaque accumulates on this stent, static pressure in the region of plaque goes very, very low. So that is one information. Can this pressure value be used to predict plaque formation in the reverse manner? That is a question that we have to answer through our research later on. If we take a normal artery and plagued artery along the same length, you can see there is a small effect, a small upstream effect of the plaque, but near the plaque point the flow character is completely different. Okay, so can this be observed through any of our pressure measurement devices, and that can tell us what people are already doing it. They say 75% artery is blocked, 80% artery is blocked. Can that information be supplemented through our CFD data further, okay, to make it more and more accurate? Here I am showing the static pressure acting on the stent, and in the normal artery with a stent you can see this is what we observed earlier. Pressure was going down here, but in this case pressure has gone far low in the stented part. This is the stented plagued part. Pressure has gone a lot lower here, so it means flow is being affected. So if you think about flow as information carrier, so flow as it goes along, it has that information, isn't it? It is for us humans to get that information. How can we get that information? Through instruments, through data analytics, or through whatever means we have. That is our job. Okay, information, you can see it is there. How we can amplify this, how we can sense this, amplify this, and use it to develop a smart stent, that is what we have to think about it now. Now this was the normal artery, and this is plagued artery. As you can see, pressure is decreasing in the plagued artery, sorry, in the normal artery. In the plagued artery it has changed. Earlier when we had normal artery and the stented artery, we got this type of behavior for normal stented artery. Now this is stented plagued artery. Okay, this is stented plagued. When I am saying normal, it means normal stented, unplagued. This is stented but plagued artery. So as you can see, the behavior is different to the normal artery. So we can see that there is a difference. Can this difference be used to say that our stent is not performing properly, and how we can do that? Okay.
Put that information through sensors, but we have to replace again.
What?
Whole stent.
So now, yeah, not only we have to replace again. If your design is such that it can self-heal.
If we design something and we have another put an patient, then after you are saying that we have analyzed the data, some after 1 year or 2 years we analyze it, we found it is not working in good condition. We get the data from sensor. Then what is the options available? We have to again replace that.
You believe in God? Do you believe in God?
Yeah.
Okay, so good. So if you believe in God, and suppose God gave you unlimited powers to do anything with this stent, what would you do? Suppose you got unlimited powers, that I can modify a stent from outside, what would you do? What? From outside, without touching a stent. You would like a stent to become smarter, isn't it? You would like a stent to do something, that plague goes away. Okay? Can we design a stent like that? That is the question. So you are answering your own question. So we want some intervention. Yeah?
Sir, in last slide we saw that because of that plague, the pressure was dipping very low. So the pressure difference must be there, must be large there.
Local pressure, what may happen is that upstream and downstream pressure difference may be same, but locally it may go down and locally, so local pressure is being affected. So that is where the global performance indicator and local performance indicator, CFD provides us that information. So globally you can get that. Okay. So thing is, can we create a smart sensor where some intervention can be carried out either in the plaque structure or plaque interaction, stent structure or stent interaction with the artery, that plaque can be melted or plaque can be removed or something can be done.
Actually, we can go the drug into the stent when
Yeah.
they are required. Thrombosis occurs.
Yeah.
Thrombocytinase enzyme will be triggered with the sensor mechanism, nanomedicine type. So when it will is unfolded, then it can dissolve the plaque.
Yeah.
Dr. Lee used to give the injection when he saw that there is a heart attack, this plaque is there. So thrombokinase injection will dissolve the plaque.
Yeah, so this is one of the interventions, but probably one thing is once we get the information, then lots of clinicians, scientists can make what judgments are needed. We engineers can contribute our bit by designing how to design such a system which can self-heal. Lots of work is being done all over the world on self-healing systems, especially self-healing electronics. So you have got electronics, a component breaks, can we reroute the circuit, that component keeps on working still. So lots of work is being done now on self-healing devices. So devices that get damaged, but they can self-heal themselves in one way. May not be with 100% efficiency, slightly reduced efficiency, but that can be done. So self-healing systems will be what really smart systems are. Okay?
How can we use the digital twin in this condition?
It's very simple. Digital twin is very, very simple thing. So you have sensor there. Sensor is giving you the pulse, pressure pulse. You have simulation running. Based on that pressure pulse, your geometry is changing. So you can see the plaque formation and all corresponding to that pulse. So it's very simple. Only thing is you have to create a cyber physical system, very accurate artificial intelligence, and very accurate simulations.
Complete system or our single artery?
What is that?
The complete whole human body we have to create a single artery in which we have put the stent.
If you can put all the computers together in the world, I'll say entire body. If you have very small computer, just take one artery. Depends on the computing power, isn't it? If you have supercomputers, we can, ultimately it will happen, but when, we don't know. Maybe 50 years, 100 years down the line it may happen, but right now we don't know. Okay? Any more questions, please? Yeah.
It is also possible to remove the stent back, if a plaque admitted on the stent, again, how can we remove the stent?
I think this is a question better for doctors, isn't it? I'm not a doctor. So, but I think there must be options to take the, like, you have to do operation again.
No, not operation. So artery incapacity is there inside pipes. Balloon system is there, then there is
So these are standard medicinal processes for that, for stenting, isn't it? Yes, any more questions, please? Now if you look at the velocity profile, you can see again here where the plaque formation took place, there the velocities are very, very high here. Okay, so velocities are high, velocity gradients are going to be higher there at that particular point. In this part there is little difference. The difference can be seen here in this particular part when the plaque formation has taken place. The plaque formation here will affect to some extent the flow here, but that effect on the second artery will be very, very small. Most effects will be on the plaqued artery, but some effect can be seen on the second artery as well, but that is second order effect. Okay. So the velocity magnitude variation along the length, near the plaqued part, you can see the plaqued artery has high velocity, and the because the area of cross section has decreased, so plaqued artery has higher velocity as compared to the normal stented artery. Now again, this is a flow information that it carries. These are the velocity profiles between the plaqued artery and the normal artery, and in the plaqued region, this part, the velocity profiles will be slightly different to the stented normal artery, and we can see the effect there. The wall shear stress on the stent in the two conditions will be completely different, drastically different. You can see here near the plaqued part, the stresses are very high. The plaqued part, the stresses are very, very high as compared to normal part. So again, the non-uniform distribution of stress in the plaqued and unplaqued artery. Now here we are showing shear stress against the P in over P baseline. So if suppose inlet pressure is varying, how the WSS, that is wall shear stress maximum for normal, this is the blue, so this is normal wall shear stress, this is WSS maximum for plaked. So you can see it is higher at the, in this part it is almost similar, slightly higher than the normal one, and then it is lower in the post plake region. The average WSS is not much different, but what you need to see here is that although the average values are almost same on the plake, the local values are different. Okay, so on average it may be same, but locally things may be quite different. So the plake deposition and other sort of interactions between the blood and the artery can be completely different locally. Here this clearly shows that in the plaked artery the wall shear stress gradients are negative, whereas in the normal artery wall shear stress gradient is positive. That is a big change, okay, from positive to negative. Now can this information be used to get information about plake formation is something that we have to explore, but based on this it shows as if the wall shear stress gradient is distinctively different for normal artery and for the plaked artery. So this can be one information that can be quite useful to at least get the location of the plake, size of the plake, location of the place, and the severity. This tells us about the vorticity magnitude. Again, near the plake formation you can see vorticity is a bit higher as compared to where there is no plake formation. So vorticity may be an indication of that. Vorticity means the three-dimensionality in the flow field. That tells us about the plake formation, and then the Q criteria values look to be different. In the stented artery, the Q criteria is significantly higher as compared to normal stented artery. So Q criteria means the difference of the vorticity magnitude minus the deformation, linear deformation. So the circular motion is much higher near the stent, and we can imagine why, because there is an obstruction, flow has to go across it, so it can cause separation and it can cause vorticity. So this is, I've given you some information about how different types of faults affect the flow field. Now next question for us is, can we get this information in a form where I can link it back through artificial intelligence, through data analytics, to tell us about the type of faults or type of formations that has taken place. For you all, I will suggest you carry out this tutorial, but then afterwards what you can do is create data bank, not for circular faults, for different types of faults, and then from the data that you get, from the results that you get on wall shear stress distribution, wall shear stress gradient, or pressure field, see can you get some unique features out of it, okay, unique features out of it. And let me tell you, there are some current tools. Have you heard about proper orthogonal decomposition? Proper POD, proper orthogonal decomposition. So a complex signal can be divided into, it's like Fourier transform. A complex signal can be divided into major orthogonal components, okay, and look at those values of orthogonal components for stented and unstented arteries and see that they give us an indication about fault. Can we link that directly to the fault? And this comes under digital signal processing. So if you can carry out digital signal processing, you can get the information about that, okay. So that is a different stream. Maybe computing people will know, or electronics people will know. We also do the digital signal processing in mechanical engineering, so it combines all these aspects. The other option is, apart from CFD, can we create low fidelity models? That is, models which are not as rigorous, but we don't have to run CFD all the time. So maybe we can run hundreds of simulations beforehand and create a data analytic tool. Put all these simulations in the memory and link these simulations with 1 or 2 indicators that we can measure on the body. So we measure those on the body and uniquely relate that with the simulations that we already have stored. So we don't have to run the simulation. Simulations are already stored for a variety of conditions. We just have to computationally access it. So it's more of a computational science problem than fluid dynamic problem. Okay. So this is also this thing is also being tried now in variety of applications. Okay. With this, I will finish this part on stent optimization and stent design. Any questions you would like to ask?